All good? Can you hear me? Yes? Try again. Okay. Okay, let's get started. Is there some event happening today or something? It's a small class. I know it's Thanksgiving, but not here. Happy Thanksgiving to everyone. So maybe that's the occasion, or the weather is too good that people are having fun. That's what it's supposed to be. I mean, you may not get this weather again soon. Yeah. Okay, so let's get started. Today we're going to continue prefetching, and hopefully we'll finish it today, but let's see. And tomorrow we'll start multiprocessors and bottleneck acceleration. Many interesting topics, many fundamental topics. Last time we started prefetching, at the last 20-25 minutes of the lecture, we gave an introduction. And we're going to look at many prefetching techniques. And a lot of these have been implemented and have been successfully employed. Still, we need more work in prefetching, and then we'll get into more researchy work toward the middle of the class, and then we're going to talk about advanced prefetchers. Does that sound good? Okay. So this is just to jog your memory. We've been talking about the memory latency problem. We've talked about that multiple times in this lecture. Prefetching is a technique to cover the memory latency. And we talked about different latency reduction, latency hiding, and latency tolerance techniques, including caching, multi-threading, out-of-order execution, and we're going to cover prefetching. This is a slide that you've seen before. What is the idea? To fetch the data before the program needs it. So it's a speculative execution method. And the goal is to, again, to cover the memory latency. Ideally, you would get the data before you need it so that you never need to access the next level in the hierarchy, caching hierarchy. Right. Okay, so we covered some of these questions. We're not going to go through them again, but we covered actually these basics. There are 4 questions in prefetching: what, when, where, and how. What addresses do you prefetch? We're going to talk a lot about that today, actually. What is the address prediction algorithm? When to initiate a prefetch request? Timeliness of the prefetcher is very much dependent on when you initiate the prefetch request. Where do you prefetch into, and where do you place the prefetcher, and where to place the prefetch data? There are many things over here, but we also discussed that separate buffers are very hard to implement because modern memory hierarchies are very complicated. So most systems today, actually almost all systems today, prefetch into caches. Okay, and then how? Today we're going to start with how. How does the prefetcher operate and who operates it, basically? And we're going to look at different methods of doing that. Okay, what's how? Essentially, there are 3 major ways of approaching prefetching. One is software, the other is hardware, and the other is execution-based prefetching. Okay, there's more people coming, that's good. Software prefetching. In software prefetching, ISA provides instructions, and programmer or compiler inserts prefetch instructions. This requires some effort, of course, from someone at the higher levels of the stack. And this usually works nicely for regular access patterns that you can disambiguate or find at compile time or at programming time. Does that make sense? Okay. Is the light too much over here? I don't know, I feel like that, but it's okay. As long as it's fine for you guys and you can see it, that's fine. So we're going to look at software prefetching, but okay, it's good. Yeah. We're going to give you some examples. This works nicely, actually, when you have regular access patterns, especially for specialized applications. In the general case, if you have irregular access patterns that are very hard to detect during compile time, this doesn't work very well. So for specialized applications, this may be good, but then we'll see downsides of it also, because this requires the software to be aware of the microarchitectural details to prefetch accurately and timely. Hardware prefetching is essentially what you think. Hardware there's specialized hardware that you add where you monitor the memory accesses. And this hardware can memorize or find or learn different patterns in the access stream, address stream. It could be stride, as we will see. It could be correlations. It could be something else, as we will see. And the hardware generates prefetch addresses automatically. Of course, you can combine these things also. You can have software, hardware, cooperative mechanisms, and we will see some of those in this lecture, where you have some hardware and the software directs what kind of stride to use, for example. Or software initiates what kind of prefetcher to use, or the software basically does something to enable the prefetcher to act more accurately, etc. There are many, many mechanisms that have been proposed in literature, and it's possible to combine these. After we cover some of these, we're going to cover execution-based prefetchers. And here, the basic idea is to have a thread that you execute to prefetch data for the main program. Usually that thread is speculative. It's executed before the main program executes a problem instruction, like a problem load that will likely miss in the cache. And hopefully when that thread executes, the main program is also executing. And by the time that thread prefetches some data, the main program has not yet gotten to the instruction that needs that data. That's the idea, basically. You can overlap the execution of the main program with the execution of the speculative thread. And the main program, in the ideal case, never stalls because the speculative thread always generates the cache misses early on. Again, the question becomes who does this, right? Who generates this? It could be the hardware. It could be the software. It could be a combination. Essentially, this execution-based is a very special case because it could be a special case of software prefetching or hardware prefetching, but it's really executing a part of the program or the main program itself to actually do prefetching. Now we're going to look at different methods of doing that. Sounds good. Okay, this is a very exciting area, as you can see. There have been many works on this topic, and this is an area that I've worked on personally for more than 25 years. As I mentioned, my first internship at Intel actually was tuning their prefetcher that they had, and I'm going to talk briefly about what kind of prefetcher they had, and also looking at what kind of accesses should be sent to the memory controller in what order from the prefetcher. So how do you order the demand and prefetch accesses on the processor chip such that you get a good access stream on the memory controller, such that you get good row buffer hit rates, for example. You've seen row buffers, you've seen DRAM. So it's good to think about that right now. If you're prefetching, and if you have demand accesses, these can conflict with each other potentially. And if you want to get good DRAM bandwidth, you may want to reorder the accesses. Okay, so there are a lot of interesting things here. Any questions? Waking up? Okay. Okay, let's talk about software prefetching. This is an idea that's been proposed many times, and there are many versions of it, but these are some of the earliest papers by David Callahan in S+ 1991 and Todd Maury in S+ 1992. And the idea, as I said earlier, is compiler or the programmer places prefetch instructions into appropriate places in the code. And these prefetch instructions prefetch data into caches or a prefetch buffer, but usually caches in real ISAs. And the compiler or programmer can insert such instructions into any place in the program. So for example, in alpha architecture, R31 was a special register, and it's essentially wired to 0. If you use load with R31 as the destination, that would actually act as a prefetch instruction. They didn't have a separate prefetch instruction, but they used a load with a destination of a register hardwired to 0 as a prefetch instruction. And you could generate any address basically with the address generation mechanism that they have, which is base plus offset in alpha. Okay, so this is the x86 prefetch instruction. They have special prefetch instructions. This is one version of x86. And you can see that there are multiple versions of the prefetch instructions. And unfortunately, the explanation, or at least the description, is not very nice. Basically, the idea is to prefetch some value into some place, right? Move data, for example, if you look at the description, move data from M8, which is a location, closer to the processor using T0 hint. Then you go back and look at what is T0 hint. There are T0, T1, T2, and NTA. And T0 is temporal data. Prefetch data into all levels of the cache hierarchy. Pentium 3 processor, first or second level cache. They have only 2-level caches. Pentium 4 Intel Xeon processors, second level cache. What happened to all levels of the hierarchy? Right. First level cache is gone from prefetch T0. Anybody guess why? Why did they decide to remove the first level cache from prefetching? Yes. Okay, that's a good one to think about. Yes. Okay, that's possible also. I don't know why. Okay. But your prefetcher can actually go through the TLB, right? But that could be a consideration. That's right. Your prefetch generation now, your prefetcher only works on physical addresses, and it never needs to go through the TLB. That's what you're saying. That's possible. What else? Yes. Yeah. Okay, that's also good. I mean, these are also all valid concerns, actually. It's good to think about them. The main reason is actually what you said. I would say it's basically L1 is actually very small, too small. And if you actually start prefetching into L1, you start displacing a lot of demands. L2 is much larger. So they actually didn't give the programmer or the compiler a chance to prefetch into L1, basically. But all of the others are considerations that you need to think about in terms of where you place the prefetcher also. Okay, so you can see other things. T1 is temporal data with respect to the first level cache, use prefetch in second level cache. So basically, this description is not that great because there's no differentiation between T1 and T2, for example. And NTA is the interesting one, I would say. Basically, non-temporal data with respect to all cache levels, prefetch data into non-temporal cache structure into a location close to the processor, minimizing cache pollution. So for example, in Pentium 3 processor, if you use a prefetch NTA, it prefetches data only into the first level cache and not into the second level. In Pentium 4 and Intel Xeon, it prefetches data into the second level cache and not into the first level cache, which is interesting, right? So clearly they're trying to reduce the pollution that happens in the cache hierarchy, but prefetch NTA has no differentiation. Prefetch T0, T1, T2, and NTA has no differentiation in one of the microarchitectures, which is interesting. But the idea of non-temporal prefetch is to ensure that the data doesn't pollute all of the caches. Okay, it's good to think about that. So even microarchitecture specification of prefetches is not very nice. Okay, and then there's another issue, like if you implement this, this is a speculative instruction, right? There's no requirement that you should complete this instruction. So if a hardware designer is running out of time to design and verify a processor, what should they cut? They cannot implement everything. They can cut the prefetch instructions. They can say, oh, okay, I'm not going to implement the prefetch instruction because it's speculative anyway, right? Its goal is performance improvement. It's not functional. It's not serving any function. Makes sense, right? It's really accelerating an access. There will be another load that would hopefully be touching the data that is also touched by the prefetch. But if you eliminate the prefetch, the load is still there. Okay? So software prefetching is in that sense interesting. It's hard to define what's a good prefetch destination, etc. But it's also easy to drop from a hardware designer perspective because of speculative instruction. That's true for all speculative instructions. You need to implement things that are important for your functional execution, the result of the program. But again, from a hardware designer perspective, you don't need to follow the specification at all, not implement prefetch, right? So a compiler generates all of these prefetch instructions. They don't do anything because they're not implemented nicely, let's say. So it's good to think about this. So it's how do you actually incorporate speculative instructions into an ISA and make sure that they actually work. Okay, let's take a look at a couple of software prefetching examples. So software prefetching can work for regular array-based access patterns. You can see one of them over here. This is a loop where you're actually summing AI and BI elements. Assume that each element is 8 bytes. We added some prefetch instructions, speculative instructions, that are prefetching for the next cache block, right? In this particular case. Am I correct? I think so, yes. Assuming 8 bytes. So it's good to think about this. There are many issues over here, right? You want to insert these prefetch instructions, and this makes sense, right? While you're operating on A0, B0, you're prefetching A8, B8, right? You started those prefetches, they don't block the processor, and they go on. The problem is, should you be prefetching A8, B8, or should you be prefetching A64B64, for example? Essentially, how far ahead should you prefetch? And how do you determine that, right? Before we get into that, prefetch instructions clearly take up processing and execution bandwidth because those are instructions that are inserted. They get translated into those prefetch NTA, for example. How early to prefetch? Determining this is difficult because it's really dependent on the hardware implementation. It's dependent on the memory latency, whether you have the data cached in some of the caches, meaning cache size, associativity, etc. It's also dependent on time between loop iterations. Right? How far should you prefetch is dependent on what else do you do in the loop. How long does a sum operation take? In this case, it's a very simple sum, but there could be actually some other operations inside the same loop iteration. So you will need to decide how far to prefetch based on all of those parameters. That's compile time, which makes it hard, clearly, right? Because how do you know all of that information? Memory latency we have seen is very variable, right? Depending on what happens. Your caching, you may not know exactly what will be in your cache. But if your program is completely regular, then you can try to figure out all of those things. It's a lot easier to figure out all of those things compared to irregular accesses. And if you actually make a mistake, if you prefetch too early, maybe you don't have the data before you get to that iteration where you need the loop, where you need that data. If you prefetch too early, then you will actually get the data into the cache much earlier. But then you may never get to that loop iteration because the loop may terminate at some point, right? Okay, so it's good to think about these. And then do you need special instructions? The ISA, I kind of mentioned this earlier. If you have a load into register 31, it's treated as a prefetch in alpha, for example. But there are other ISAs that have special instructions like what we have seen with Intel x86. Like PowerPC had a data cache block touch instruction. It's kind of a nice name, right? You touch the data cache block. And that's treated as a prefetch instruction, essentially. Okay, any questions? No? Otherwise, let's take a look at where this doesn't work very well. Irregular structures, essentially. If everything is regular, you can try. But I guess even if everything is regular, there's an issue, which is the portability of code. You compile this code for some architecture with some memory latency, with some cache size, with some associativity, with some cache replacement policy. And then you optimize this beautiful code and your prefetchers are generated at the right time, let's say. That's great. Now, if you port it to some other architecture with some other memory latency, some other cache size, etc., the same code, the same optimized code doesn't work too well, right? Because your optimization is really fundamentally microarchitecture dependent. So this is the code portability issue. Not portability in terms of functionality, but portability in terms of performance. You may optimize one for one architecture and the code is great, and you run the same code on some other microarchitecture and the code runs like a dog. So it doesn't work, basically. I mean, it doesn't, your optimizations are essentially useless potentially, right? So it's good to think about that. And this actually opens up a lot of issues. How do you actually ensure that your code is portable in terms of performance across microarchitectures? You can, of course, do this compilation dynamically, potentially. If you do dynamic binary optimization, dynamic compilation, you can actually optimize this code. But again, there are overheads to dynamic optimization. Yeah. Any thoughts? Okay. Okay, let's take a look at some other program, some other, let's say, piece of code. This is a linked list traversal. As you can see, you're doing some work on the data of this node, and then you're moving to the next node. And then you're repeating this until you reach the end, until P is null, basically. And you add this prefetch instruction for P next. Does this work? It could work, assuming P next is. So basically, your address is dependent on P, right? So the P points to your current linked list node, and next provides the address of the next linked list node. So you have some address calculation that you need to do based on that. If that's in your cache, this prefetch can go ahead, and maybe you can overlap the latency. Okay, that's fine. You basically prefetch for the next iteration of the loop. What if I want to prefetch beyond the next iteration? I do this, right? Now, the problem is this is a linked list traversal that you're doing, P next, next, next. This is 3 iterations ahead. And for this, you need calculations, essentially, right? So you cannot do this, essentially. Because if you do this, then you're actually executing the next iterations of the loop without doing the work, right? So this pointer chasing is a problem. It's one example of potentially irregular accesses. But if you really want to do this computation, you'll need to do something else. Maybe, for example, you have a separate loop that just goes through and prefetches next, and then you do the work on the data. It's good to think about this basically. But this doesn't work because, yeah, essentially you're waiting for this to complete first before you do the work on this. Okay, so people have developed actually special prefetchers for pointer chasing that we will see soon. This is a hard problem. It's not an easy problem because of what you have seen, dependence on the next address that you need is dependent on the previous address, which is dependent on the previous address, which is dependent on the previous address, which is dependent on the previous address. So this sort of execution calculation does not work very well. Okay, so basically what I'm getting at is where should a compiler insert prefetches? So this is similar to what we've discussed earlier, but then there's a more fundamental question. What do you prefetch for, right? Do you prefetch for every load that you're going to see? The downside over here is every load is not going to miss in the cache. So maybe it's useless to, it's actually very bandwidth intensive in terms of both memory bandwidth as well as execution bandwidth. Or do you profile the code and determine loads that are likely to miss? That's what most people do in compilation, as well as if you do it dynamically. So you try to figure out which loads are going to miss in the cache, and you try to prefetch only those. You could determine this using profiling, or you could determine this using some analysis, right? Static analysis of the code, assuming some microarchitectural parameters, assuming your accesses are really, really regular, and you can model things nicely. Static analysis may work fine. But if your accesses are somewhat irregular, you have a lot of other things in your cache, etc., then you may need to profile. Of course, with profiling, if you profile and you figure out this load is going to miss a lot of the time, let's say 90% of the time it's executed, when you actually run the program with a real data set, when the program is actually running, that may not be representative, right? That load may never miss with the real data set. So you have always the issue of profile input set representativeness with profiling. So these are some of the issues with software prefetching that you need to be aware of. There's another issue actually that's also interesting, which is related to this part over here. Where is this? Yeah, portability again. So you optimize your program and you prefetch. Yeah, let me go back to portability. You optimize your regular program nicely. You insert the prefetch instructions, and the program is running nicely when it's run by itself. Okay, it's running by itself. It's that you have all the cache to yourself, and it runs perfectly because your prefetches are optimized for that. Now, when the program runs with some other program, and they're sharing the cache, your optimizations are essentially potentially useless because you don't have the cache and you have more interference. So you've seen this problem when we talked about memory controls, interference, right? So interference actually interferes with these memory optimizations that you do because what you've assumed at compile time is not true at runtime, right? Okay, so it's good to think about these, which is very similar to profile input set representatives in a different way. What you assume at compile time is not true at runtime, right? Okay, there's also the question of how far ahead before the miss should the prefetch be inserted. Again, you can profile and determine the probability of use for various prefetch distances from the miss. You can determine this analytically by doing program analysis, assuming you have regular access patterns and a lot of things. Or if you have irregular things, you need to figure out, if you have an irregular execution, you need to figure out where to insert the prefetch. Again, you can do this via profiling. You can basically say, oh, I'm going to insert the prefetch at distance, I don't know, 10 instructions before, 20 instructions before, 30 instructions before, 40 instructions before. For all of these, you're going to profile the program and run it and figure out which distance makes sense. Right? You can even run it through a simulator if you want. You can run it through a real machine, etc. So basically, this becomes even harder, right? It's a more expensive form of profiling now. Where do you insert the prefetch? And if your profile input set is not representative, and it's more likely that this will not be represented because this depends on not just the load instruction missing in the cache, but what else happens in the execution stream, right? How long it takes. So in the end, prefetch placement is not easy, especially for irregular programs. Where do you place the prefetch? Usually you need to insert a prefetch far in advance to cover hundreds of cycles of main memory latency. And once you start doing that, you raise the prefetch much earlier in the program, and your accuracy starts reducing because you start prefetching And then there's some control flow graph, and you never reach the load that you actually are prefetching for, because you took some other branch that took you somewhere else in the code. So if you actually do the prefetching too early, you risk your timeliness increases, but your accuracy and coverage reduces. Okay, so a lot of things to think about. And this is exactly why it's not easy to do software prefetching for irregular programs. Regular programs, even then there are issues that we discussed. So people have developed a lot of hardware prefetchers, and we're going to cover some of these. Any questions on software prefetching? Am I thinking? Writing. Okay, so here we're going to design specialized hardware that observes load store access patterns or cache miss access patterns and prefetches data based on past access behavior. And we've seen some access patterns last time. Now we're going to see how to capture them in hardware. So there are, of course, trade-offs over here also, like with every idea. Here, the good news is you don't need to change the ISA. You don't need to waste extra instruction bandwidth. And you can tune the hardware to the system implementation, because you're designing the microarchitecture anyway. Why not actually design the hardware, hardware prefetcher that is customized to the microarchitecture? That's the idea over here. You can tune the hardware prefetcher. But of course, this requires more hardware complexity to detect patterns now. Before, the software was telling you which addresses to prefetch. Here, the hardware needs to detect patterns itself. And in some cases, software can be much more efficient, potentially. Okay, so we're going to see some example ideas. These are some early ideas, next line prefetchers. This was developed in 1960s. This is the simplest form of hardware prefetching. And the basic idea is always prefetch the next n cache lines or cache blocks after a demand access or demand miss. Depends on when you trigger, right? You access cache block A, you always prefetch cache blocks A plus 1, A plus 2, A plus 3, A plus 4, ... A plus n. That's the idea. This is called the next line prefetcher. It's also called next sequential prefetcher in old literature. And n is, of course, important to think about. It's very simple to implement. Here, there's no need for sophisticated pattern detection, right? You always prefetch the next n cache lines. It works well for sequential or streaming access patterns. Then the question is, what are those? Instructions, for example, if you keep going through the instruction stream, it's very sequential, right? If you keep going through an array, that's very sequential. So those kind of access patterns, it could work well. But then there are issues also. It can waste bandwidth for irregular access patterns. Here, next line assumes that you keep going through the next line, right? What if that assumption is not true? You always access the lines, cache blocks with a stride of 2, for example. Right? Then you're still prefetching. So if you have a stride of 2, and if you're prefetching next 1 cache line, let's say n is 1, you're not covering anything, right? You're basically generating a lot of prefetches. None of them are used because your access pattern is n, n plus 2, n plus 4. What you're doing is when you get n, you prefetch for n plus 1. When you get n plus 2, you prefetch for n plus 3, right? So you're always prefetching something that you're not going to use. Your accuracy is 0. Your coverage is 0. Your timeliness is irrelevant, basically, right? Doesn't sound good, right? So this is the problem, basically. You have to somehow, it's very rigid. It cannot adapt to the access pattern. And this is a still regular pattern, right? So if you cannot do this regular pattern, how do you actually deal with irregular patterns, right? Maybe you need to get lucky, basically, with irregular patterns. Okay, yeah, I already said this, actually. And even with regular patterns, I think I've given you this example over here. And then there's the other question. This is next n line. What does next mean? Is it increasing addresses or decreasing addresses? What if sometimes you're traversing from high to low addresses, and sometimes you're traversing from low to high addresses, right? Direction, basically. This is called the direction of prefetch. Do you also do next, let's say, n lines from the other side, lower size, like a minus 1, a minus 2, a minus n? Yeah, so this becomes quite bandwidth intensive at some point. So these are actually developed. They're very easy to implement, but you need to really know your access pattern and direct the prefetcher. So if you somehow have a classifier, for example, that decides, okay, for this part of the program, I should do a next line, maybe this could work. But as a general prefetching mechanism, it's not very, let's say, desirable for the reasons we discussed. That's why people have developed stride prefetchers. Like I've already given you an example of this, right? A plus 2, A plus 4. More generally, it's A plus N, A plus 2N, dot, dot, dot. Here, the stride is N, right? And you can easily detect it with a little bit more hardware than next line prefetchers, right? The idea is to record the stride between consecutive memory accesses. And if the stride is stable, use it to predict next M memory accesses, right? Hopefully that makes sense. So you record, for example, A plus N, you record the stride as N, and then you see A plus 2N, oh, okay, stride is constant, build some confidence. And the last time I've seen addresses in this vicinity, I got a stride of N. So I'm going to predict that N is going to continue, and then you can keep repeating. So building some confidence is important. Okay, there are two types of these stride prefetchers. One of them determines a stride on a per instruction basis. Basically, for every load and store, you may have a stride. The other determines a stride on a per memory region basis. Basically, you don't have the information of the program counter or load or store. You just look at the data access stream, data addresses, and you try to find the strides. It's kind of like that, basically. I didn't say anything about which program counter generated that address A plus N, etc. It's whatever you see on the data side. And they're both implemented in real processors, actually. Let's take a look at instruction-based stride prefetching. Essentially, you need to have a mechanism for detecting the strides, which is indexed by the program counter. So for a given program counter, you need to keep track of the last address referenced or missed, depending on which access stream you're looking at, misaddress stream or access address stream. And then you have the last stride that you've seen when you last encountered this load. And then you have a confidence for that last stride. So you can implement this as a table lookup. Each load instruction can lead to a memory access pattern with a different stride if you actually do that. And you can distinguish between those different strides easily, assuming each program counter has that behavior. I mean, they may also have the same stride, of course, but you can still distinguish that this load is generating each stride X. Now, the downside of this, or maybe upside potentially, it can only detect strides caused by each instruction, right? If there's some stride that appears because 2 instructions are interacting, or 3 instructions or 4 instructions are interacting in some way that doesn't appear for each instruction, then you cannot capture it. That's the idea. Timeliness of prefetches can always be an issue, as we have discussed for software also. If you initiate the prefetch when the load is fetched, the next time, this can be too late. So you need to actually have some look ahead. So if you're executing this load, it depends on when you're executing this one instance of the load and the next instance of the load. Is there enough time to prefetch for the next time? Right? So if there's not enough time, you look ahead in the instruction stream. Basically, you prefetch for the next nth instance of the load. You multiply the stride by n, for example, and add to the base address so that you actually look ahead and prefetch for the nth instance. Right? So you need to determine the timeliness. Hopefully that's clear. Memory region-based stride prefetching is very similar, except you have this table that's more indexed with a region address or cache block address. You look at a region, that's the address tag, region meaning a larger, coarser granularity. It could be a page, for example. It could be a virtual memory page. You look at that region and you basically associate a stride with that region. That's possible. So if in this page, for example, the processor is always accessing the cache blocks with a stride of n. And this n could be happening because of a single program counter or because of some interaction across multiple program counters. You don't care. What you're observing is, what is the stride in this memory region? I don't care about the program counter in this case, right? So this is also interesting because this has the capability to detect strided memory access patterns that appear due to multiple instructions. Yeah, basically, you have stride where each access could be due to a different instruction. If you look at a single instruction, you may not capture this, or you may not capture this as easily. Stream buffers, which we're going to talk about, or stream prefetching, is a special case of memory region-based stride prefetching where n is equal to 1. You basically access the next line. Maybe not so interesting, but it's still implemented. It's actually a very powerful paper written in 1990 by Norm Juppy, which we will see. Okay, so basically there are trade-offs in all of these decisions. We cannot cover every single trade-off that we make clearly these prefetchers, but as I've already told you, the latter, meaning the memory region-based stride prefetching, can exploit strides that occur due to multiple instructions. The latter can more easily get ahead of the demand access stream, although you still need to be careful. You still need to try to get ahead. There's no need for some look-ahead program counter, although you could eliminate the look-ahead program counter. The latter is more hardware intensive, because if you look at program counters, there are a small number of instructions. Usually, there are much smaller number of instructions that you go through when you execute a program than the number of data accesses, right? So data is usually much larger, meaning data addresses there are many more data addresses to monitor than instructions. Okay, it's good to think about it, but these instructions, these prefetchers are employed. This is actually one of the earliest papers in SC 1991 from Baer and Chen, Jean-Luc Baer and Chen, Team for Chen, on instruction-based stride prefetching. It has one mechanism of doing this using look-ahead program counters. You can look at it in your homework. And this is Intel's instruction-based stride prefetcher. They use it only to prefetch into the level 1 data cache. So they need a very accurate prefetcher, because L1 data cache, as we discussed earlier, is very sensitive, right? A lot of the decisions we make in how we design an L1 data cache, it's really dictated by the pipeline, because it needs to be tightly integrated into the pipeline, and you need to get data very quickly to supply the load instructions so that you don't stall the pipeline, right? And as a result, L1 caches are usually small, very few cycles to access, and you need to manage the budgets of hardware very carefully. So if you prefetch inaccurate things into L1, you're going to reduce the hit rate in L1. So Intel actually implemented this IP-based prefetcher. There are many other companies that have implemented this also. And later, toward the end of this lecture, we'll talk about some more some prefetchers that are IP-based. Any questions? So these are real, basically, these implementations. That's the key takeaway. A lot of what we're going to discuss is going to be real, including some of the ideas that were thought to be too hardware intensive in early 2000s, and they made their way into products, like content-directed prefetching, as we will discuss the idea. And then now people are discovering a lot of side channel issues related to these prefetchers. I think Genome is interested in that. Okay, so a memory region-based stride prefetching is also published. This is Jupi's paper. I consider at least Jupi's paper as one example of memory region-based stride prefetching. And this is stream buffers. I'll go through this relatively quickly, but basically, you could actually implement this in a nice way, assuming all your access patterns are regular. You have these stream buffers that are FIFOs. In this case, this is really where you prefetch into. Each stream buffer holds one stream of sequentially prefetched cache lines. On a load miss, you check the head of all stream buffers to see if there is a match. So your load instruction missing the decache, you look at all the stream buffers, only the head, to see if there is a match. If there's a match, then you actually pop the entry from the corresponding FIFO and update the cache with the data, and then change the head of the FIFO to the next line, essentially. So it's a next line prefetcher, except it's divided into potentially different streams. These streams can be different regions in memory. Actually, they are different regions in memory. Otherwise, you allocate a new stream buffer with a new misaddress. And you may have to replace one of the stream buffers clearly. So there needs to be a replacement policy. And the idea is to have stream buffer FIFOs continuously topped off with subsequent cache lines whenever there's room and the bus is not busy. So this is very automatic. This is assuming a very regular next line streaming access pattern across the regions, right? You start streaming, you get a cache miss from a region, and you start topping off cache block A+1, A+2, A+3, A+4 into that FIFO. And whenever you access A+1, you top off one more from the to the tail of the FIFO. Okay, this is one very particular implementation. It works nicely for access patterns that fit it. Again, if you have an access pattern with a stride of 4 or 2, you're in trouble. You need to modify the hardware, and you need to modify something else. So certainly people have proposed, okay, can we actually modify this for strides? And you can actually amend this such that FIFOs don't assume a stride of 1. You just detect the stride for each region, right? And each of the stream buffers, each of the FIFOs operate using a different stride that's detected for that region. And these are actually proposed in literature, predicted directed stream buffers, for example, from Brad Calder et al. In 2003, etc. There are many works in this area. So people did not stick to this particular design. Okay, this is the original stream buffer design, but it's very simple, essentially. You always have the next address, which is associated with the head of the FIFO, and then you increment it. That generates the prefetch address. And you essentially, the stream buffer is a small tagged buffer that buffers cache blocks. Again, this is from the original paper, if you're interested. Okay. So this actually resembles streaming prefetchers in Power 4. I will not go through this in detail, but a lot of modern processors have some sort of streaming prefetcher, and along with it, many other prefetchers. But this description, the Power 4 paper in 2002, shows essentially the streaming idea. It's not essentially, they don't describe exactly how many stream buffers they have in this particular picture, but they basically logically describe that while you have cache blocks or cache lines L0 and L1 in level 1 cache, you actually have this is, I guess, L1, L2, L3, L4, L5 in the level 2 cache, and then you keep prefetching into L1. You're prefetching L1 into level 1, line 1, I should say, line 5 into level 2, and then you can see that line 20 into level 3. And they're actually prefetching next 4 cache lines from memory to level 3 because they can be more aggressive in level 3 because level 3 is huge, right? That's the idea over here. But this is essentially a streaming prefetcher. Maybe not exactly implemented the way that Juppie described it. So this is IBM Power 4, by the way. That was the first multi-core system, at least that we know of, that is out there. So we're going to have the multi-core lecture tomorrow, depending on how we go today. So it's good to remember Power 4. Okay, this is a recommended paper. This is probably what will be one of the review papers, stream prefetching. It got the ISCA Influential Paper Award, I think, in 2005, because it was published in 1990. Okay, it's good to also look at some things in this paper, you know. This paper talks about the memory latency problem to motivate why we develop prefetchers. And you can see some of the old machines over here, VAX 11780, which is a real machine, which is designed by Digital Equipment Corporation and was essentially the machine of its time. You can see that the missed cost is 6 cycles. And cycle time is 200 nanoseconds. That's a very low frequency. And missed cost in terms of instructions is 0.6. So you waste 0.6 instructions during that miss because the cycles per instruction is 10. And then WRL Titan, Western Research Lab, Digital Western Research Lab Titan is what Norm Juppie was working on. And they actually designed something with a much faster cycle time, but memory time, there's also memory time. You can see that memory time is 540 nanoseconds, which is actually much higher than what we had because there are actually a lot of things that you need to do to get to memory, off-chip memory. And missed cost is 12 cycles. And in terms of cycles, in terms of instructions, 8.6 instructions. So you can see that the missed cost is increasing both in terms of cycles and instructions. So we have talked about memory latency in lecture 9 or so. Today, we're actually much higher in terms of cycles. 70 is very low. If you're at 70, that's great. We're at 500. In Xbox 360, for example, it's an old machine, but it was 650 cycles. That's not unheard of, 650 cycles of access latency. And in terms of instructions, actually, costs are even higher. So that's why prefetching is really important. And you can see that it was motivated this way even in 1990. Okay, let's talk about some other prefetchers. Locality-based prefetchers. These are actually things that I worked on in my first internship, my first year as a PhD student. Essentially, the problem is in many applications, access patterns are not perfectly strided or streaming. Some patterns look random to close by addresses, essentially. The question is, how do you capture such accesses? There are many ways you can think, but I call these messy access patterns. Messy meaning M-E-S-S-Y, not the coherence messy, but messy access patterns that are not easy to prefetch based on streaming or striding, etc. So there's no regularity that you may find. So this paper that we wrote in 2007 describes one of such prefetchers that is actually implemented at Intel. And the idea is to do some locality-based prefetching. Maybe it's best described by doing something here. How do you pull this up? Is there some? No, manual. Okay, this is manual. Oh, this is not the other room. The other room is not manual, right? Okay, and maybe you can help. So I'll give you the general idea, not an exact implementation, of course. But what happens is, actually, maybe you can go to the next page and we can keep it. Let's keep it so that people can see. Okay. Oh, people can see it. Okay, that's fine. Yes. Okay. Yeah. So, okay, they can still see it, I guess. So you get an address A. We're talking about cache block addresses, and you basically index into some table. That's a memory region table. That's called memory region table. To see if you have a tracking entry for that region of addresses. Region could be a page. In a lot of Intel implementations, it was a single page actually, but it could be larger than that. Let's assume it's a page. Going through page boundaries actually requires physical to virtual address translation that was discussed earlier, right? You need to figure out, yeah, you need to have a reverse address translator potentially. What happened? Okay, this is always an issue, but that's okay, don't worry. Something is happening. Okay, basically, this is a miss on some cache level. Maybe it's an L2 cache level to address A. And you try to figure out, oh, have I seen this address region before? And if you haven't seen it, what you do is you basically have a tag. Okay, I now have a region A. Let's call it a region A. I have some access to this address A, and the address is around this region. So you create a tracking entry. And now you're going to monitor accesses to this tracking entry. And maybe, again, based on the implementation, you're trying to look at addresses that span A minus 16, let's say, and A plus 16. Basically, you're trying to determine where the processor is going. Next address you get, let's say, A plus 5. Okay, now you actually, again, index into this table. Oh, this matches region A. And actually, it's in the monitored region, which is basically 16, 16. And it's somewhere here, basically, A plus 5. Oh, the processor access missed, again, on access A plus 5. Okay? Now you have some idea. Oh, the processor is probably going to the right, meaning plus direction. And it's doing some accesses. Let's monitor a little bit more. The processor accesses A plus 7. There's no stride, as you can see, plus 5, plus 2. Oh, the processor is still going this way, so I'm going to increase my confidence. You're more confident, so okay, your direction is plus, and you're confident twice that you're going this way. Right? And then the processor accesses, let's say, A plus, 11. There's no regular stride still, right? Now you're really confident that the processor is going somewhere this way. But there's no regular stride, and confidence level is 3, because you've seen 3 accesses that are after A in a plus side, and there's no regular stride. And you want to capture this, right? And you have resources, let's say. So in some of the implementations of these prefetchers, what the prefetcher does is, let's say after 3, it says, okay, I'm very confident that I'm going in this direction, in this region. So I'm going to start prefetching very aggressively to capture the next miss, because next miss is going to cost me a lot, potentially, right? And then you start prefetching. This is, again, a design decision. Maybe you prefetch, for example, everything over here, A plus 1 to A plus 16, right? We basically prefetch a lot. And if the prefetcher accesses A plus 1 next, that's great, right? Or if the demand accesses, if the processor accesses A plus 1 next, you prefetch that, right? If it accesses A plus 15 next, you prefetch it. If it accesses A plus 13 next, you prefetch it. So that's the idea over here. You don't know exactly stride because maybe it doesn't exist, but you know the direction and you know the region, and you're trying your best to prefetch for those. And then you, of course, need to move the window, meaning, let's say you prefetch for A plus 16. Next, you start monitoring maybe also the next 16 cache blocks. So you start monitoring the next 16 addresses. So if the processor accesses, for example, A plus 31 over here, you still prefetch these over here. So that's the idea. Again, exact implementations depend on how it's implemented, but these tend to be quite bandwidth intensive. You've seen that for my explanation. You actually prefetch a lot. How many prefetches you generate is your prefetch degree, and how far ahead you actually prefetch is your distance. So those things you can play with. Okay, maybe we can go back if you know how to go back. Or maybe you're already back. Okay. Yeah. So this is an example of a locality-based prefetcher. This is actually fascinating because this sort of prefetcher was not published in literature. Our paper, whose function was not the goal, our goal was not to publish this particular prefetcher. Our goal was to do something else, as we will see discussed throttling. But we actually published how it works, and we actually put it out. But Intel actually has a nice publication, as you will see. So this is the paper. Everything's okay online? Okay, good. Okay, this is the paper. And Intel actually analyzes in their, even though they didn't give enough detail of how it works, they analyze the benefits of this prefetcher. And they actually work well in real life, especially in single core systems. So this is Intel's paper. It's a beautiful paper that talks about microarchitecture of the Intel Pentium 4, Daryl Boggs and all. And you can see that on these workloads, enabling the hardware prefetcher improves performance from anywhere to 16% to 97%. Now, granted, some of these are quite regular, like eQuake. It's an earthquake simulation, and it's quite regular. So the downside of these prefetchers is multiple. One is they're very bandwidth intensive because you need to prefetch a lot, right? And there are mechanisms to actually reduce that bandwidth intensity. So people have developed prefetch filtering mechanisms, for example, to reduce the bandwidth intensiveness of these prefetchers. Like feedback mechanisms can also help. That's why we have actually developed the feedback-directed prefetching that we will talk about later on. Stride detection can help. You can eliminate perhaps some of the strides if there's some stride that you can detect. But if you cannot do something regular, this prefetcher actually works well. The other downside is because they're bandwidth intensive, when you actually have a lot of memory bandwidth pressure in multi-core systems, they actually hurt performance of other cores, for example. And we're going to talk about the impact of prefetching on multi-core. And the other downside or limitation of these prefetchers is they're limited to prefetching somewhat close by addresses, right? We talked about there's some window that you monitor. In the end, you're limited by how large your region is, right? It determines both your aggressiveness as well as what you can detect. So it's good to think about this, basically. You may have multiple regions, and as you keep prefetching on one region, you may start overlapping with other regions that you actually have created. So you run into an interesting problem with these prefetchers. There are two potential matching entries in the region. So sometimes you need to clean up this region tracking table. Good to think about how these work. Okay, any questions? This is an example of Intel's good days, as you can see, right? Intel actually did a lot of in my opinion, good ideas that are not actually developed in academic literature. Today, they're having a little bit bad days. Yes, go ahead, please. Stride-based prefetcher for a what? Mm-hmm. Yeah.
In order to predict which data will be accessed by that code in the next code,
yes,
we need to know how that data is tied and distributed in the software detail. But then we are again doing this in hardware, and we might not have a way to know that.
So you're proposing basically designing a prefetcher for a particular core for that. I mean, it's certainly possible. You can have a private prefetcher for that core, right?
But then we won't have any way to determine the stride, right? Because the stride would depend on how we have distributed the data. How many things are processed by one code in your application, which is again oftentimes determined by how we have written.
That's true, yes. Certainly, you basically partition your software, but there could still be a stride. So what you're doing in the hardware prefetcher is you're just looking at the access stream coming from that core. So if the access stream has some regularity, you'll capture the stride. If the access stream doesn't have regularity, I agree. If you partition your work such that there's no regularity, then you may not get the stride. I agree. Yeah. So certainly partitioning and memory allocation affects the kind of stride that you get. In fact, there are nice papers that talk about how to reorganize your data such that your prefetcher works nicely by creating strides. There was this paper from Intel again. It's called MS Delta, Mississippi Delta prediction. And they essentially designed a garbage collector that would work for Java programs that would reorganize the data such that you would get more regular strides. We were inspired by it and some of their work. Yeah. So what you're getting at is actually correct. How you partition your data and how you organize your data affects the access patterns. Okay. Okay, now we've been talking about regular and somewhat irregular patterns. What else? So for simple regular patterns, stride and stream prefetchers work well. Complex regular patterns, you can also design prefetchers that could capture this, like 1, 2, 3, 1, 2, 3, 1, 2, 3. We're going to see how to do that. You can have irregular patterns like data structure traversals, indirect array accesses, random accesses, if you can capture those, and multiple data structures that are accessed concurrent. So you can come up with many different patterns. Let's look at one pattern. You have multiple strides. So multiple strides is similar to this: +1, +2, +3, +1, +2, +3. That's repeated. So this is one example from a real application of how the stride changes across execution time. It could be a single load. It could be across different loads. Doesn't matter. Essentially, you can see that there is some regularity, right? After you see 7, you see -6. After you see 12, you see, after -6, you see 12. So you can correlate between the addresses that you see consecutively. So that sounds good. So if you design, this is called a correlation prefetcher or delta correlation prefetcher. We're going to see the address correlation prefetcher a little bit later, but I wanted to look at this first. And the idea is to predict which delta would come based on the previous delta that you have seen. That's a pattern detection again. So a complex but predictable set of strides. This is one paper that talks about this and proposes one mechanism to do this. So the key idea is, given a history, signature, or pattern of strides, learn and predict what stride might come next. So, for example, you can also have, essentially, you can think of this as a key value, right? The key is the previous strides that you've seen, value is the next stride that you expect to see. The key can be these 3 things that you have seen. You see 7, -6, 12, and you hash them in some way. And then based on the previous executions, you predict 6 will come next. Right? So you can, this is again table-based prediction. So keys could be of size 3 in this case, and values could be of size 1. Or it could be size 2 or size 3, meaning you predict the next, and next stride also, right? That's the idea. So that's the general idea. I'm not going to go through the details over here because there's a lot of, but basically what I said is true. You have a history of strides, you predict something. And then you use that for the next prediction, potentially, index the table again, or you store 2 predictions. Both are possible. Now, as you keep doing this more speculatively, your confidence reduces, of course, because you're kind of looking ahead into the stream. So at some point, you decide to stop, right? So you need to throttle in some way also. But this idea is actually delta correlation prefetching, and it's implemented in many modern processors also. In some way, this is one implementation of it in that paper. Okay, that paper is also from Intel. You can see that Intel did a lot of good work over many years, especially in these areas. I wish they were publishing more papers these days, because once they go belly up, hopefully we won't lose all of that useful information that's stuck inside the company, you know. Or worse, some other company takes it and destroys it. Okay, so now let's talk about more irregular access patterns. So we're going to talk about correlation-based prefetchers. You already saw an example of delta correlation. We correlate the deltas, right? But correlation-based prefetcher is actually much more powerful than delta correlation, because you can do address correlation. And in this case, you don't need to have any repeatable relationship. Well, you need some repeatability in the end, but you don't need to know the strides, etc. The relationship between addresses A and B doesn't need to have a particular stride. Okay, and then we're going to talk about content-directed prefetchers, and then we're going to talk about pre-computation or execution-based prefetchers, which are even more powerful. Although there will be trade-offs in terms of like where do you execute these things. Okay, this is address correlation. Essentially, it's similar to delta correlation, but we're going to work on addresses. If you look at the following history of cache block addresses, you can actually draw some conclusions, right? After referencing a particular address, some addresses are more likely. For example, after referencing address A, B is more likely to be referenced next, right? You can see after address A, B appears multiple times. Sometimes A appears after A, sometimes C appears. Yeah. So you can actually develop a Markov model by seeing these addresses. These could be miss addresses, or this could be hit addresses, or all kinds of addresses that you see in a cache. And this is the Markov model, basically. It basically says, for example, after seeing B, with 100% probability, you will see C. So there's a strong correlation between B and C. After seeing A, with, I guess, 20% probability, you will see A again, and with 60% probability, you will see B. And what happens after that? Oh, there's also the remaining probability is C, 20% over here, as you can see. That's forgotten here. We should fix that. This slide has been used many times, but that 0.2 for some reason disappeared. Okay, so you can develop this model, and the idea is basically, if you have this sort of model, you can represent it in some hardware structure. It could be a table, and you can represent the probabilities also. Now it becomes expensive, of course. And whenever you see address A next, you say, okay, I'm going to prefetch C, or no, B, because that's the highest probability. But I'm also going to prefetch, let's say I'm not going to prefetch A because it comes after itself. I'm also going to prefetch C because maybe it'll happen also, because I have extra bandwidth, right? So that's the idea, basically, of a Markov-based prefetcher. So this is one implementation of it. And this was proposed in the seminal paper by Doug Joseph and Dirk Grunwald in 1997, prefetching using Markov predictors. So you index things, index the table with a cache block address, and there's a tag, of course, associated with it. And then you have prefetch candidates listed alongside with it. For example, after seeing address A, you have 3 prefetch candidates, B, C, D. This is different from what we have seen earlier. So next time A is accessed, you see A, and then you, so the first time A is accessed, you actually record what you see over time. You populate this with B, C, D, and you can record the confidence level also, which is probability. And next time you see A, you can basically access all of these prefetch candidates, and you will find B, C, D with some confidence level. And A is now correlated with B, C, D, right? So in this table you store it, and then you can prefetch up to n next addresses to increase coverage. So whenever you see A, you prefetch B, C, D. Of course, this is bandwidth intensive if only one of them is going to come after that, right? Okay, to increase coverage, you can do that, of course, but then this hurts accuracy, right? If you prefetch all of them. So you now see the trade-off, hopefully, is you become more aggressive, your coverage increases, your timeliness likely becomes better, although this is a bit different. But again, still, usually your timeliness becomes better, but your accuracy drops. You can also improve accuracy by using multiple addresses as key for the next address, right? As opposed to using just A, you wait for A and B. And every time you see A and B in sequence, the next address you see is C. So now A and B are said to be correlated with C, right? Very similar to delta correlation in the end. But this was developed before delta correlation. And this is actually very intensive in terms of storage. Why? Because you need to store a lot of addresses, right? Now, where does this work really nicely? Okay, these are also called Markov prefetchers. So the big advantage is it can cover arbitrary access patterns that are repeated. Right? So like linked data structures. For example, you have a linked list, A, B, C, D, E, F, G, H, I, J. You keep doing the entire alphabet. And then you go back, you traverse the linked list completely. And then later in the program, you execute a loop that traverses the linked list again. You already recorded what addresses come after each other. So the next time you traverse the same linked list, you're going to get all hits, hopefully. That's the idea. Now, if you want to do that with a billion entry linked list, you're in trouble because you need to store all of those correlations across billion elements, right? And that's the problem with the hardware intensity of these approaches. It can cover also streaming patterns. You know, this is actually very powerful. If you do, for example, or striding patterns. Let's say you're doing A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, A plus 6, A plus 7. You don't need to represent this access pattern as a stride. You can represent it as correlations. A is correlated with A plus 1. A plus 1 is correlated with A plus 2. A plus 3 is correlated with A plus 4. You can represent as a huge table inefficiently, and it can still prefetch. But of course, clearly representing this as a stride is much more space efficient compared to representing as a table with correlations. So you can cover a lot of patterns. That's the upside. Well, of course, there's a lot of disadvantages too. Correlation table needs to be very large for high coverage because it needs to record every misaddress and subsequent misaddresses, sometimes multiple times, assuming how you organize the keys and values. It can have low timeliness because you initiate a prefetch for the next access right after the previous, but you can improve this, of course, right? By being more aggressive. You can basically index into the table once, get the prefetch address and index again. You can speculatively index the table with prefetches, right? So that's possible to improve timeliness. And it can consume a lot of memory bandwidth, especially when these probabilities or Markov model correlations are low. And that's in general a problem. Actually, all of these apply to, except for the correlation table, apply to delta correlation-based prefetchers as well. So if you have delta correlation, the representation is much more compact, right? And you could actually, with delta correlation, you could also represent streaming and striding patterns because the delta is the same in that case, right? Okay, so one of the other disadvantages of this, at least address correlation, is it cannot reduce compulsory misses. What does this mean? If you've never seen an address, you've never recorded it, so you cannot prefetch for it, right? So that's one downside. Another downside of this over a stream-based prefetcher or stride-based prefetcher. A stride-based prefetcher doesn't need to see A+1, A+2, A+3, A+4. It just needs to latch on a stride, and at some point, it generates addresses that are never seen, never demanded. But here, if you want to capture the streaming patterns with an address correlation-based prefetcher, you need to record every single address that you've seen, right? In the strictest sense. So compulsory misses are always a problem with these prefetchers. Although that's not true for delta correlation. If you do delta correlation, you don't need to see the address, you just need to see the deltas. So that's the power of delta correlation. These are actually good questions to think about. Okay, yes? No, that's a design choice, basically. You know, you'll need to decide based on how critical that prefetch is for you, whether you have the resources to waste, potentially. Yeah. Usually what happens in prefetching is if the probability is very low, people drop the prefetches for good reason, because they're wasting some bandwidth or energy, right? Especially energy is important today. Yeah.
So that is design choice in the, even that is dynamic.
It could be dynamic, yeah. A lot of the design choices can be dynamic. Thresholds can change, and thresholds can be adaptive. For example, a lot of the prefetchers adapt to the memory bandwidth availability. If there is not enough memory bandwidth, they basically throttle to lower. We're going to see throttling. But yeah, a lot of the decisions are dynamic, but some of the thresholds may not be dynamic. I mean, ideally, we would like to make all of these dynamic, and that's why we're going to talk about using machine learning to actually design prefetchers, which Rahul has done part of his PhD thesis on. So if you do that in a more methodical way, you can adapt to the workloads in a much better way. Okay. So let's talk about content-directed prefetching also. This is actually a very creative idea, in my opinion. I was at Intel when this was being developed. I didn't develop it, but people at Intel, whom I respect a lot, developed it. It's essentially a specialized prefetcher for pointer values. And the idea is very simple. Identify pointers. So you look at a cache block, and you identify pointers among all values inside the cache block. And if something looks like a pointer, you basically generate prefetch requests for them. Does that sound good? Now, the question is, how do you identify pointers? This is actually Bob Cooksey, ASP+ 2002. It was rejected multiple times also before getting into ASP+. It's a beautiful paper. But basically, the huge advantage of this is you don't need to record anything. Everything that you're looking for, at least with this mechanism, is inside the cache block. The data values inside the cache block, some of them are addresses because they point to some data structures. That's the idea. So it's very low cost. It can eliminate compulsory misses, never seen pointers, basically. The program never touched a pointer, but it's inside your cache block, right? So you can actually generate that address. Now, the downside is, at least the way it was proposed, it indiscriminately prefetches all pointers in a cache block. Now, some of them may not be useful, right? So we're going to talk about how to fix that problem. But this doesn't make it a bad paper, basically. It's an idea paper. It basically shows that some idea may work. Now, of course, there are multiple questions over here. How do you identify the pointer addresses, right? And this paper proposed a clever mechanism. I mean, you could, of course, identify the pointers by software support, right? You could say, if some data value is a pointer in memory, there's a tag associated with that particular value associated with the cache block or associated with memory, and that tag indicates it's a pointer. It could be part of a load instruction, etc. So you could actually identify it with some software support. But the goal over here was to do it without any software support. And the idea is you can scan the entire cache line and you look at pointer-sized values, because not every value, depending on the ISA you're using, sometimes pointers are 64 bits in general. That's the case today. So you look at all 64-bit size values, and if the most significant bits of that 64-bit value that you look at matches the 64-bit address that you use to access this cache block, which is the cache block's address, then you declare that as a pointer. It's a speculative mechanism. It may not be correct. You're basically banking on the fact that the top level bits of an address that you're accessing matches the top level bits of an address sized value. If that's the case, that address sized value is really a pointer. Hopefully that makes sense. I'm going to show you an example of this. Of course, this is done in the virtual address space, because pointer chasing is assuming you have virtual memory, which is the case in most systems today. Pointer chasing happens in virtual addresses, and the data cache blocks store those virtual addresses. So there's a virtual address predictor. Assume that you access this address, virtual address, x800 blah blah. You get the data from DRAM, and this is the cache block. This is your address, x800 blah blah, and these are 8 pointer-sized values. And you basically compare the top n bits. I think in this case, top 12 bits. And these, if the top 12 bits match, in this case they match, as you can see. The other ones don't match. Then you take that address and generate a prefetch. Of course, you need to go through the virtual to physical address translation, right, to do this. So that's the idea, basically. Sounds good, right? Very clever. Of course, now if all of the values start with x800, you generate prefetches for 8 of those values, right? And then there are other design decisions you make. Okay, I generate a prefetch for x800 blah blah 11100. Okay, I got the cache block. I haven't used that cache block for anything yet. Do I scan that cache block also after it comes back? So you have a depth, basically. So you can actually keep generating prefetches speculatively by scanning the cache blocks that are brought in by prefetches. So you can get ahead in different ways. But then the problem is, if you have a lot of pointer values inside your cache, if you have a lot of pointers inside your cache, you're going to be prefetching a lot. Okay, so controlling this is really important. And this is something that we have worked on. This is part of Iman's thesis at UT Austin. And the idea is, again, controlling this is not easy. So we actually have a hardware-software cooperative mechanism. Hardware doesn't have enough information on pointers, and software does. And software can profile to get more information. And the idea is here to have the compiler to profile or analyze the code and provide hints as to which pointer addresses are likely useful to prefetch. And it can guess that based on the structure of the program or based on profiling information, as we will see soon. And hardware uses these hints to prefetch only the likely useful pointers. Basically, you need to add another bit to either a load instruction, as we did here, or cache block. Somehow you need to decide which pointers inside the cache blocks are likely useful. It's like a bit vector that's supplied with every load instruction. And you only prefetch for those likely useful pointers. Let me give you an example. This is a minimum spanning tree program, and you basically do some hash lookups over here. Essentially a linked list traversal whenever you do hash lookups. This is a part of the linked list. So it looks like this, essentially. You hash, and then you go into a bucket. And in this bucket, you do a linked list traversal. And you can see that the linked list traversal is searching for a key. Again, you can think of it as a key value pair. And then you're looking for values, right? And these are all pointers. There's a next pointer that goes to the next node. And if the key matches, you do something with D1 and D2, or you return D1 in this particular case, right? So the idea over here is to ask the question, what is a useful pointer? Right? Assume that these linked lists are long, and you're searching for a key. Once you actually go into a bucket, the question is, what is the probability that you're going to use the next pointer versus the probability that you're going to use D1 and D2? I guess you never use D2, so you can eliminate that. So you can eliminate prefetching that D2 pointer by just looking at this code, right? You should never prefetch D2, at least in this part of the code, because the code is not using that, assuming that ... doesn't use it, but it doesn't. Well, it doesn't, yeah, because anyway. Okay, D1 is less likely to be used than key because you're going to use D1 and return that pointer, that data value associated with that pointer, only if the key matches. First of all, key may never match, so you do a linked list traversal of a 1,000-entry linked list, which means that D1 is not going to be even used once. And if it's going to be used ever, its pointer should be prefetched only once, right? That's the idea. So what is the most frequently used thing? That's really the next point. So you should really prefetch only the next pointer if you're trying to save your bandwidth, and never prefetch D2 pointer, and maybe once prefetch D1, but maybe that's not as important. So that's the idea basically. But if you actually do this with the original like content-directed prefetching proposal, this is how your cache blocks may be laid out. You prefetch essentially everything except for the key, because they're all pointers, right? And with a more intelligent proposal, you prefetch only the next ones. Okay, that's the idea. Some animations are unfortunately broken over here, sorry, but that's the idea. You prefetch the useful pointers, but for that you need to collect information about the usefulness of a pointer. You could collect it, as I just showed you, just observing the data structure, right? This is called program analysis. And we semantically look at what is being accessed, etc. Or you could do it via profiling. For more irregular access patterns, profiling is easier, of course. And this is a paper, if you're interested in looking at it. Okay, let me cover hybrid hardware prefetchers, and then we're going to take a break. Essentially, hopefully it's clear to you by now that different prefetchers have different capabilities, right? This content-directed prefetcher is not going to work well for streaming accesses. It's not designed for it either. It's designed for a very special purpose, right? As you can see, this is a very special purpose prefetcher. And all prefetchers have upsides and downsides in terms of what access patterns they cover. That's why people use hybrid hardware prefetchers today. And in a modern processor, you see, I don't know, I don't want to name the number, but more than 10 prefetchers. I can guarantee you that in many processors. But in some cases, maybe close to 10 prefetchers. Also, sometimes depending on what you consider a prefetcher. Do you consider off-chip predictor a prefetcher? Okay, we'll think about that. Okay, basically you use multiple prefetchers to cover many memory access patterns. This enables better prefetch coverage, potentially better timeliness, because you're distinguishing between different access and deciding what to prefetch with. But of course, now you have more complexity. There are many design optimization decisions. Every prefetcher has some tuning parameters, and now you have many prefetchers you have to tune. This is more bandwidth intensive, clearly, because you're trying to prefetch a lot. Potentially, you're activating multiple prefetchers. And prefetchers can interfere with each other also. They cause contention, pollution to each other, as well as to demand requests, as we will see. So you need to manage accesses from each prefetcher, and you may need to throttle them independently. Okay, that brings us to prefetcher performance, but that's probably good to cover after taking a break. Any questions? Okay, let's take a break until, what is that? 15, that's 45, 50, 50 past. And then we can continue with prefetcher performance. Is it the right one? All good? Okay, good. Okay, let's continue now. Now that we covered a bunch of prefetchers, we're going to cover more later, but let's talk about prefetcher performance because it's really important. And there are many metrics to measure prefetcher performance. In the end, execution time of a prefetcher is really, how much a prefetcher affects the execution time is really important, of course. But there are also some auxiliary metrics that affect that execution time. And there's also energy consumption that's added because of either added execution time or wasted requests. So there are three metrics to measure performance, which we've covered, but we're going to define them. Actually, we defined some of them. Accuracy is the number of used prefetches divided by number of prefetches sent. Coverage is number of misses that are prefetched out of all of the misses in a program. And timeliness is how many prefetches are on time divided by how many prefetches are used. And essentially, timeliness can be a binary metric, but it could also be scale, right? Because what fraction of the memory latency you're covering is a question over here. So timeliness measurement is not easy in that sense, but it's good to keep that in mind. There's also bandwidth consumption and cache pollution that are also metrics. Bandwidth consumption is memory bandwidth consumed with the prefetcher divided by memory bandwidth consumed without the prefetcher. So the good news is, even if you increase bandwidth consumption, this may not be bad for performance because you may be utilizing idle bus bandwidth that no one is going to use. Good luck finding that these days. It's not easy because memory bandwidth is one of the major bottlenecks that we have in many applications and many systems today, but it's possible. And cache pollution is, these are the negative effects of the prefetchers but bandwidth consumption, extra bandwidth consumption always increases energy because you're consuming more energy, at least at that level, right? You may reduce energy because you're executing the program for shorter, but bandwidth, increasing the bandwidth increases the memory energy you're consuming. Okay, cache pollution is another issue with prefetching. Extra demand misses, this is essentially measured as extra demand misses due to prefetch placement in the cache. It's a bit more difficult to quantify, but affects performance, right? Because, yeah, you need to basically keep track of whether a prefetch evicted a demand miss that's going to be used later, right? Because you may evict a demand miss that's not going to be used potentially, right? Okay, so essentially prefetch aggressiveness affects all performance metrics. Aggressiveness is really dependent on the prefetcher type, what kind of prefetcher, and we've seen a lot of types. And for most hardware prefetchers, there are two major knobs that affect the aggressiveness: prefetch distance and prefetch degree. Prefetch distance is how far ahead of the demand access stream that you're getting. If the demands are, let's say, and this is actually not an exact measure, but with stride prefetchers or with regular prefetchers, it's easier to think about this, or streaming prefetchers. If the processor is accessing address A and you're doing, let's say, streaming A+1, A+2, A+3, the prefetcher is operating at address A+16. So the assumption is it's already covered 16 ahead. It's going 16 cache blocks ahead of the demand stream, right? And that's the distance. So distance is 16 in that particular case. And prefetch degree is how many prefetches do you send for demand access. So this is very different. How many whenever you get a demand access and you decide to prefetch, how many prefetches do you send out? So pictorially, this is your access stream. Access stream may be accessing X, and this is a predicted stream, which is what your prefetcher has done. And the prefetch distance is how far ahead of the access stream the predicted stream is. So this is an aggressive prefetcher. This is a very conservative prefetcher. Let's say the predicted access stream is very close to the access stream. This is a middle of the road prefetcher, and this is the very aggressive prefetcher. So you can see that you can pictorialize these things, right? Make sense? Okay. And the prefetch degree is, let's assume that you get access X, what do you prefetch? Or X+1, what do you prefetch? You get new access in the access stream, you prefetch P+1, P+2, P+3. That means your degree is 3. So clearly degree can be aggressive, very conservative, middle of the road, or it could have actually a continuum of degrees. Okay? So the question is basically, how do you actually set the parameters of your prefetcher? There's also how do these metrics interact, right? Very aggressive prefetcher. You can have a large prefetch distance and degree. Very conservative prefetcher, small prefetch distance and degree. And as a result, very aggressive prefetcher would be well ahead of the load access stream, which hides the memory latency better. It will be more timely, but it will be more speculative also. Whereas very conservative prefetcher is closer to the access stream. It may not hide the memory access latency completely. And being very conservative clearly reduces the potential for wasted bandwidth and also polluted caches. So in general, a very aggressive prefetcher has higher coverage, better timeliness, but likely lower accuracy, higher bandwidth, and higher pollution in general. Whereas a very conservative prefetcher is likely higher accuracy, lower bandwidth, and less polluting, but likely it has lower coverage and it's less time. Makes sense, right? So based on everything we discussed, hopefully that's clear. So we've done a lot of studies on understanding the effects of these metrics on actual performance, system performance. So this picture shows an example. This is where we look at prefetcher accuracy on the x-axis, and the percentage IPC, instructions per cycle change, over no prefetching. Basically, how much the prefetcher is improving performance. You can see that there is some correlation, right? If your prefetcher is terrible in terms of accuracy, you don't improve performance that much, or you lose performance. If your prefetcher is better in accuracy, in general, you gain performance, but not guaranteed, right? Hopefully that makes sense. So accuracy is, this tells that there's some correlation, but accuracy is not the only metric to think about, right? Okay, so you can draw similar things with coverage, timeliness, and you can draw more complicated graphs with coverage, accuracy, and timeliness, which you cannot read and hope that AI reads for you. I don't know, but he can do things essentially. So in this work, basically, we wanted to decide the accuracy, decide the aggressiveness of the prefetcher dynamically, as opposed to setting the prefetcher to have fixed prefetch distance and fixed prefetch degree. We wanted to dynamically change the prefetch distance and degree across different levels, basically. So let's take a look at first what happens to different programs if you do no prefetching, which is the baseline, which is 1.0 essentially in terms of instructions per cycle. These are single core results. Or do very conservative prefetching, or middle of the road prefetching, or very aggressive prefetching. You can see that on average, this is geometric mean of IPCs. These are not normalized. This is actually real IPC for some processor. You can see that improving the aggressiveness, increasing the aggressiveness of the prefetcher improves performance. But at some point, you get diminishing returns. Middle of the road and very aggressive are not that different from each other. Right? And the main reason is, for some applications, going from middle of the road is very aggressive is actually good. You keep improving performance. Where's my favorite? eQuake, earthquake simulation. This is a +1 stride, for example. It's very nice. You keep improving aggressiveness. You actually get better performance. That's not true in all workloads. For example, there are 2 workloads where if you keep becoming more aggressive, you keep losing performance. Right? So here, actually, no prefetching is better. Here, very conservative prefetching is slightly better than no prefetching. So you can see that different workloads behave differently. And also within a workload, different phases or different parts of the workload, when they execute, behave differently. So if you have a dynamic way of adapting these parameters, you would actually do better, hopefully. And for this, you can do ideal studies, etc. Or you have an idea and you implement something and see if it works. Because ideal study may be very difficult to do over here, because you need to explore all of the dynamic options. What's the ideal parameter, right? Okay, so the idea of feedback-directed throttling of a prefetcher is you dynamically monitor prefetcher performance metrics, and you throttle the prefetcher aggressiveness up or down between different levels of aggressiveness based on past performance, based on these metrics, basically. And in addition, you can change the location the prefetchers are inserted in the cache based on past performance. Performance means these metrics. For example, if the prefetchers are expected to be not so accurate, maybe you inject the prefetchers at a lower priority into the set so that they don't evict demand misses. Right? That may be more useful. If the prefetchers are expected to be very accurate, maybe you inject the prefetchers or insert the prefetchers into a higher priority, like MRU position, because they're expected to be used and accurate. So, okay, the paper has more detail, but this is kind of a decision tree-based mechanism, threshold-based decision tree mechanism. No machine learning here. So if you're, for example, if the prefetcher is highly accurate, it's not late, but it's polluting, you decrease the aggressiveness because it's polluting. And it's not late, so maybe it'll be okay if you decrease the aggressiveness, right? If the prefetcher is high accuracy but late, we increase the aggressiveness so that it becomes less late or more timely. So these are some design decisions that we made based on, let's say, our experience and also some simulations that we run. It's basically threshold-based heuristics. You could replace some of these things with machine learning, which may be better actually, but we didn't do that in this work. And again, if the prefetcher has medium accuracy, not polluting, but late, we increase the aggressiveness so that it becomes less late, let's say. If it has medium accuracy, but it's polluting, then we decrease the aggressiveness. And you can basically form the full decision tree, which is in the paper, which I'm not going to talk about. But for example, yeah, if you have no change if it's this way, but otherwise, if it's low accuracy, you decrease the aggressiveness. So accuracy is important, as you can see. Okay, so if you do all of that, and if you implement this sort of throttling mechanism, this is what we find when we simulate these workloads with a better prefetcher. So this is no prefetching, and this is very aggressive. So I don't throw the middle of the road here, which was in the previous picture. So on average, if you do feedback-directed prefetching with dynamic aggressiveness and dynamic insertion policy into caches, you improve performance better than very aggressive prefetching, as you can see. And more importantly, you actually improve performance compared to no prefetching in these workloads where you were losing a lot of performance. Hopefully it makes sense, right? So you basically cut your losses, and you don't lose much in those workloads that are doing well with very aggressive prefetching, although you lose a little bit, so you could do better actually, potentially compared to this. So this is one example. This doesn't show what's the potential on top of this, of course. There may be more potential actually, because we could do more finer grain adjustment of these thresholds. You could do prefetch filtering on top of this, etc., but we didn't do that. Okay, what is the impact of this on memory bandwidth? Essentially, we're going to measure the memory bandwidth in terms of bus accesses, memory bus accesses per 1,000 retired instructions. This includes the effect of a lot of things, including L2 demand misses as well as pollution-induced misses and prefetches. And this is a good measure of memory bus bandwidth usage, actually. So this is what we find. We're plotting both, well, in this table, we're showing both IPC and bus accesses per kilo instructions. And you can see no prefetching, very conservative, middle of the road, very aggressive, and feedback-directed prefetching. And you can see that feedback-directed prefetching is better than very aggressive prefetching on average IPC, while also reducing the bus accesses per kilo instructions. So this is good in terms of both performance and energy. And it's actually, if you look at the middle of the road, its performance looks like this. So it's a bus access per kilo instructions similar to feedback-directed prefetching. So compared to a system with similar bus access per kilo instruction, you're getting a lot more performance. But middle of the road is not good because some applications degrade a lot, right? It's good to think about that. Clearly, if you are not prefetching, you have some level of bus access per kilo instructions that's much lower because you're not spending that bus bandwidth on prefetches. But even very conservative prefetching, you can see that is good for IPC a lot. So you can see diminishing returns happening. Okay, so hopefully this gives you an idea. So this is why feedback-directed prefetching is employed in some form in essentially all processors. All processors have prefetchers. All processors have throttlers that are based on feedback. There are many works, if you can ask Rahul, for example, many patents from many companies that cite this paper and that work on principles based on this. But we're going to see that some of these principles need to be amended when you actually are in multi-core systems. Then you need to take into account more information about what else is going on in the system. You cannot just take into account accuracy, coverage, and timeliness like we did in feedback-directed prefetching. You also need to know what harm are you inflicting to other processors, because you may be actually delaying them, right? You're using memory bandwidth when they need the memory bandwidth, and you need to take into account the memory bandwidth availability also. So there's some later work by Iman again on hierarchical prefetching aggressiveness control that improves upon this and makes it adapted to the multi-core. And existing systems actually have that sort of information also in prefetchers. So if you're building hardware prefetchers, you need to throttle them. That's the key takeaway. Does that sound good? But this doesn't mean that these are the best techniques. I think there's more room for improving hardware-based prefetch management, or maybe more generally hardware-based prefetch and demand management and scheduling going into the future. Oh yeah, this is the paper that actually adapts us to the multi-core and makes it work. Here you need more complexity. What happens is you need to actually take into account these other metrics, like whether you're doing harm to some other processor, some other core's demands, how much memory bandwidth is available. But then that actually increases the number of thresholds that you have, right? You need to consider more things and you need to have more thresholds. So all of these mechanisms are threshold based, and you need to set a threshold. And setting that threshold, if you set that threshold, I don't want to call it wrong, but not necessarily well, then you don't actually make a great decision. So the thresholding is actually an Achilles heel of these mechanisms in general. Okay, there's more work in this area that I'm not going to talk about, but you can find. These are actually more multi-core related works. So, which brings me into multi-core issues. So why should we consider multi-core a little bit separately? Well, because there are different issues in multi-core. Because prefetching efficiency, I'll start with the second one actually. Prefetching efficiency is a lot more important. Let's start with the second one. Because bus bandwidth is more precious, right? Multiple cores are really demanding things from the same memory. Cache space is also more valuable because they're shared caches. And in these shared structures or shared media, one core's prefetches interfere with other cores' requests. So you can get cache conflicts at multiple levels. You can get bus contention at multiple levels. And you know very well that you can get DRAM conflicts at different parts of the DRAM, right? So it becomes a lot more important to, let's say, throttle the prefetches such that you don't run into these problems. There's also another issue, which is prefetching shared data, right? If you have shared data and you're keeping the caches coherent, which we're going to talk about in later lectures, how to do that in more detail. Now, one processor may have some data that it's accessing. And how do you prefetch that shared data? When do you prefetch it, right? If you prefetch some shared data too early, you bring the data to another processor. But this processor who had the data in its cache maybe is going to use that data and write to that data. So you actually prefetch something inaccurately because you didn't wait until the other processor finished what it was doing, right? So prefetching shared data is actually important, and it affects multiple processes or threads that are sharing data across the hierarchy. Make sense? Okay. So I will not go through all of these in detail, but there's more work in bandwidth efficiency. So bandwidth efficiency is really important in multi-core. And we've done a lot of work, and you can take a look at some of these works. Okay, maybe I'll go skip these also. If you have time, we're going to talk. There's also prefetching in GPUs. Here, actually, memory bandwidth is even worse. Then the question is, how do you prefetch in GPUs? And again, I will not go through this in detail, but a lot of people turn off prefetchers or do not even design prefetchers in GPUs. But more and more, as GPUs start running irregular programs, they have actually turned into prefetching also. And you need to actually design the prefetcher very carefully. Any questions? Okay, so I'm going to talk about some like forward-looking ideas where we apply machine learning to prefetchers. You've seen self-optimizing memory controllers in an earlier lecture by Mohammed, right? Or was it me? No, I don't remember. But it was you. Yeah, that's right. It was me last year, which is a fascinating work, no question about that. And the question is basically, can you actually apply similar principles to other parts of the system to make the system much more adaptive to the workload and also the system itself? So this is Rahul's work. Do you want to give this? Okay, I'll go ahead. Okay, and he published this in Micro 2021. And this actually spurred a lot of work on prefetching and machine learning-based prefetching afterwards. And it's also completely available. I should have put the data prefetching championship slide somewhere here. Okay, I'm going to remind me to remind people. Okay, I forgot that. It was in my mind when I was preparing slides, but yeah, it's inspired a lot of work. So we're going to talk about that relatively quickly. And the idea is basically to apply reinforcement learning to the prefetcher design. And you've seen reinforcement learning earlier. This is an algorithmic approach to learn to take an action in a given situation to maximize some reward. Right? So you have an agent that interacts with the environment. It observes the state of the environment, and it takes an action. It learns that in this state, if you take this action, that's going to lead to a positive reward, which means improved performance, for example, right? And if you keep learning the relationship between state action pairs and expected rewards, you can actually find what action to take in a given state to maximize your reward. That's the idea, basically. And there's a lot of reinforcement learning mechanisms to do this. In this particular paper, we look at Q-learning, similar to what we have done in self-optimizing memory controllers. The agent stores some quality values for every state action pair. Of course, every state action pair, you quantize the state, and you normally don't quantize the actions, but potentially you could do that. But in this case, you don't, because state may be huge, right? You quantize the state so that you can index a table that stores state action pairs. And this gives you the expected return for taking an action in a state. And you learn basically, if you take an action in a state, for example, the action could be prefetch this address. In a given state, prefetching this address is good because that prefetch is going to be used. That's the idea. So you can train this reinforcement learning agent. So you can give in a state, you select the action that provides the highest Q value. So that's the idea. So why do we want to do this? Because this actually, if you have a framework like this, in which you put prefetching, then a lot of the design decisions boil down to what is your state, what is your action, and what is your reward. So you don't need to design a, let's say, very specialized prefetcher. Although this is going to be a bit specialized to something, but you don't need to exactly provide an algorithm for detecting a stride, for example, right? Hopefully the reinforcement learning algorithm is going to do that for you if you set up the problem in a nice way. So this also reduces the designer's burden in coming up with an algorithm that's good. The burden, of course, shifts to defining the problem such that the reinforcement learning agent can learn nicely, right? Now that's the burden of the designer. Very similar arguments like what we had for memory controllers, if you remember self-optimizing memory controllers. Okay, and I think there's a lot more potential in this area because this particular prefetcher is going to do some sort of prefetching, like offset-based prefetching nicely, but we don't know how to do other forms of prefetching, do we? Okay, Rahul agrees that we don't. Yeah, there's a lot of potential based. Okay, so basically Pythia formulates prefetching as a reinforcement learning problem. Your agent is your prefetcher. Your environment is a processor and memory subsystem. And state is a vector of features of memory requests to address A, for example, program counter. It could be last few cache line deltas, etc. And action is basically an offset. The action is to prefetch from address A plus offset O. And among many different actions, meaning different offsets, the prefetcher decides to prefetch the offset that provides the highest Q value, highest expected return, or multiple offsets that provides the N highest expected returns, right? That's a more generalized mechanism. Okay, and then it gets a reward saying that this prefetch was good or bad, and it trains those tables that store the Q values associated with the state action pairs. That's the idea, basically. Very similar to what we have seen in self-optimizing memory controllers, except it's a different problem, so you need to customize the solution to the different problem. So I'll go through these relatively quickly because the details are important, but we don't have a lot of time to go through every detail. So what kind of features do you look at? The features can be control flow based, data flow based, and you can do feature selection like we did earlier with memory controllers. So you basically come up with a lot of potential features and then figure out which features are really most important for this problem. And for that, you need to do a lot of simulation, for example. PC, branch PC, last 3 PCs can be control flow features. Data flow features, the address of the cache line, physical page number, delta between 2 cache line addresses, last 4 deltas that you have. These are actually information that may be important to decide offset O, right? That's the idea. You can come up with hundreds of features and then do feature selection. How many did you come up with? 16? Okay, at least. So there's more potential over there too. Maybe you come up with more and maybe you'll get a better Pythia. Okay. And then in the end, there's some features that are selected. I think you have 2 features, right? Okay, we're going to get back to that, I guess. What is action? Action is a bit easier. Essentially, given a demand access to address A, the action is to select prefetch offset O. That's the setup of the problem, right? This is a particular type of prefetcher now, offset-based prefetching. Now, action space, assuming you're keeping within the page, a 4 kilobyte page and 64 byte cache time, you have 127 actions, right? A zero offset means no prefetch is generated, and we further prune the action space by design space exploration. This is the part that makes the prefetcher a little bit less adaptive, because you prune some of the offsets that you think are never going to appear in a program. But if they appear, your prefetcher is crippled because you cannot prefetch for that offset, right? So you can see that there are trade-offs that you need to make. And the reason to prune the action space is because your tables become large, right? Because we're storing state action pairs, and you quantize a state. You don't want to quantize it too much. You don't want to quantize the action because that goes back, that takes you back to square one, kind of. Although you could quantize the action and make your prefetcher a little bit aggressive, meaning you have some action interval and you prefetch everything among that thing. That's possible also. But again, the goal is to make it implementable as well. Okay, what is the reward? This is actually one of the critical things in general, as you have seen with also memory controllers. What is the objective? How do you actually update the Q values, right? And in this case, the reward encapsulates prefetch usefulness and also system level feedback. And there could be many, many things that you want to encapsulate. Rahul developed something that encapsulates the memory bandwidth usage as system level feedback. And let's take a look at the reward level. So there are 5 distinct reverse levels. If the prefetch is deemed to be accurate and timely, you get some reward. If it's accurate but late, you get some other reward. If it's some coverage loss, you get some other reward. If it's inaccurate, there are 2 cases. If it's inaccurate and there's low memory bandwidth usage in the system, you get some reward. And if there's high memory bandwidth usage, you get some other reward. And these are 2 different cases, because if you're inaccurate and you don't need that much bandwidth, maybe that's okay, right? I mean, it's bad, but it's maybe okay. And but if you are inaccurate and if you actually need a lot of bandwidth, meaning you're using a lot of bandwidth, that's probably much worse. That's why we distinguish between these levels. So these are actually designer's burden in the end, right? Designer needs to actually come up with these levels, and there's no prefetch, and you can ask Rahul for more. And these values are determined at design time via automatic design space exploration. It can be customized further in silicon for higher performance, as we will see for some applications. So for example, these are, there's one reward configuration may be biased toward generating accurate prefetches and taking bandwidth-aware prefetch decisions. So it looks kind of like this, right? Essentially, accurate prefetches, whether they're late or timely, get positive rewards. Timely gets even higher rewards, as you can see. No prefetching gets, let's say, okay, sorry. No prefetching gets some close to 0 reward, let's say. Inaccurate and high bandwidth usage gets a very negative reward, punishment, let's say. And inaccurate and late, inaccurate and low memory bandwidth usage gets a negative reward that's worse than no prefetching. So basically what you're optimizing for is accuracy over here. You prefer to generate accurate prefetches. And you prefer not to prefetch if the memory bandwidth usage is low, as you can see, right? Because not prefetching when the memory bandwidth usage is low gets a lower negative reward than inaccurate prefetches under the same condition. And you strongly prefer not to prefetch if memory bandwidth usage is high, as you can see, right? This way you can steer the prefetcher to make the decisions that you think are important. But again, these are designed by the designer. So maybe automating these actually is a good idea also, right? It's good to think about these. Ideally, if you can explore the design space with more automation, that's good. Or maybe actually do these, change the reward function dynamically. So there's a lot of possibilities over here to look at, especially with today's machine learning systems, right? Okay, Rahul says right. Okay, so if you want to do something different, maybe you know something about your workload, for example, you may want to customize the reward function, right? For example, if you know that your workload is very, very negatively affected by inaccurate prefetches, you may actually do this. This is kind of the basic configuration designed for general workloads. And your workload is very negatively affected by inaccurate prefetches. Your inaccurate prefetch rewards are much more negative, and your no prefetch rewards are positive now. So you're biasing the prefetcher to choose actions that are accurate or not prefetching. That's the idea. Okay, I already said everything, I think. And this may be useful in server class processors, for example, or bandwidth sensitive workloads like graph prefetching, graph workloads that we have discussed, for example, in processing in memory, TCuARCH, for example, if you remember the paper. In many of these cases, actually, either the processor designers or the system designers or people who run the workloads turn the prefetchers off because they know that they're going to lose benefit. They're going to lose performance, or they're not going to gain performance. They're going to waste energy, etc. But if you have this sort of adaptive mechanism, when you're running general purpose workloads, you have some reward function. When you're running these really intensive workloads, you have this other reward function, and you don't need to change the hardware, right? You basically change the reward values with the same hardware. So that's one benefit of a framework like this. It enables you to customize the reward function to the workload, potentially. Right? That's the idea. I already said that. So this is the basic Pythia configuration that is evaluated in the paper. I'm going to give you some results. So you can see that the actions are pruned into only 16 offsets. And rewards are like this. That's the basic one that we have seen. And there's more detail on how you actually do this. I'll go through this relatively quickly, but essentially, it's a table-based mechanism. You record all Q values for state action pairs. And there's an evaluation queue of recently taken actions so that you can evaluate whether a prefetch is used or not used, for example. A demand request comes, you assign a reward to a corresponding evaluation queue entry. And then you generate a state vector based on what your state. And then you look up the Q value store. And then you figure out which action has the maximum Q value. And you generate a prefetch based on that offset, essentially A plus O, if you remember. And then you insert the prefetch action and state action pair in the evaluation queue. And when the evaluation queue entry is evicted, you update the Q value store by examining whether that prefetch was used, right? Okay. So, and when a prefetch fill comes, you set the fill bit if essentially it's fill bit. Okay, I went through this relatively quickly, but hopefully the ideas are there. There's more detailed implementation in some other slides in the paper. Make sense? Okay. So let's take a look at the performance of this. This is Rahul's evaluation with a lot of cores. Well, as cores increase, you can see the geometric speed up over no prefetching. And these are state-of-the-art. Are these all spatial prefetchers? They're all spatial prefetchers. Are they the best previous ones? Okay, best previous ones at the time, right, in 2021. Or the paper was, I guess, 2021. Yes, that's correct. Okay, you can see that prefetching improves performance, but as you get more cores, the performance improvements over no prefetching is not very high. So Pythia improves performance under all configurations. And even with many cores, you can get significant performance improvements. So these are the exact numbers, but you can read the paper for more detail. Okay, and its gain increases with core count compared to prior best prefetchers. Okay, so this is another interesting picture. What happens if you have varying DRAM bandwidth on a single core? On the x-axis, you have DRAM mega transactions per second that you have available to the core. On the y-axis, you have geometric mean speed up over no prefetching. And these are the curves that you get for state-of-the-art prefetchers. And if your bandwidth is very limited, as you can see over here, you lose performance compared to no prefetching. And this is kind of the workloads that we're kind of talking about. So if you look at, these are the real systems with per core bandwidth values. This is our baseline, which is actually quite ample bandwidth at the time again. And this is what Pythia buys you. So if your bandwidth is very limited, you don't gain much performance, but you don't lose either. That sounds good. And if you have more bandwidth, your performance is still higher than any prior prefetcher. Okay. So you actually gain a lot compared to existing prefetchers, but maybe in these bandwidth values, they should be turned off. Okay. Okay, so if you actually do the customization we talked about, so you know some workloads are very sensitive. Graph analytics, for example, they're very sensitive to wasted bandwidth. So you don't want to be prefetching aggressively, and you're inaccurate. You change the reward function such that you are more biased towards accurate prefetches or no prefetching, and you try to avoid inaccurate prefetchers like the plague. You actually gain some additional performance compared to basic Pythia. Basic Pythia actually buys significant performance in these workloads. But if you customize the reward, basic Pythia is the basic reward function that we showed. If you actually customize the reward function for these workloads, you get a lot more performance, as you can see. So there's more potential over here. I don't know if you customize the offsets over here. You didn't customize the offsets, so maybe you customize the offsets also, and you make the offsets more programmable. So there's actually a lot of potential ideas over here. I don't like pruning the offsets in general. I already said this many times to Rahul, but there's more work to be done in this area. So in my opinion, there's a lot of potential. So can people implement prefetchers like this in the data prefetching championship? Okay, that's good. Okay, there you go. But I mean, to improve this, yeah. So you can actually, here's a challenge for you. Maybe you can make a much better prefetcher and you can win the championship. And you get to go to Sydney and present. Sydney in January 31st sounds good. On January 31st. Okay, basically you can get higher performance via customization without changing the hardware. So always the question is, at what cost, right? Everything, there's nothing that comes for free. And Pythia has some cost. It's not negligible because you need to have these tables, right? And these tables, I think, according to Rahul's evaluation, is about 25 kilobytes per core. So if you actually have more offsets, that actually blows up. And he modeled it using hardware description language. And you can see that there's area, power, overheads, etc. Okay. And this is all open source. People can develop on it. And there's a longer video that Rahul has. And there's a lot more in the Pythia paper. And if you're interested, again, in participating in the championship, I would recommend looking at this and maybe improving Pythia, because I think there's a lot of potential for this. Maybe I'm biased, but what do you think? You agree? Okay. So do you think this would be the winner of the championship if someone figures out how to make it much stronger? Yeah, that's true. Yeah. Yeah. But you got to think creatively because your competitors will be thinking similarly potentially. Okay. Any questions about Pythia? Yes. Oh, okay. Mm-hmm. Yeah. Mm-hmm. Yeah, yeah. Do you want to take that? Was it tried on GPUs? I don't think so. Yeah. Yeah. Yeah, yeah. Yeah. Yeah, it's good to think about this. Yeah, I'm not sure if a lot of works try GPUs because GPUs are very bandwidth sensitive, and there's very little work, in my opinion, on prefetching on GPUs. Like we've done some work that I flashed. In general, there's very little work. I think there needs to be a bit more, especially with irregular workloads on GPUs. Okay. So if you're interested in more reinforcement learning, this is Sutton and Barto's book, updated book. These guys recently won the Turing Award for reinforcement learning. It was a bit late, I think, but they did win it. That's good. This is actually a very nice book. The nice news is they actually included our memory controllers as one of the applications, successful applications of reinforcement learning. That's optimizing memory control over here, 16.4. Pythia came after this was published, so maybe in the next edition they will include Pythia. I don't know. Let's see. Yeah. So there are of course more some other applications like AlphaGo, which has had a lot of, let's say, publicity because I think they won against real human players, right, in the Go game. Okay, so the question is always, can we do better, right? And I'm going to talk about another of Rahul's work, another application of machine learning to memory hierarchy management, and a form of prefetching also. Essentially, you have prefetching and caching. They're commonly used latency hiding techniques. And with Pythia, we have observed that 50% of the memory requests are saved from going to main memory. What about the remaining parts? Can you do something about them? Of course, you can develop better prefetching algorithms, right? Or make Pythia better, augment it with different things, have hybrid prefetchers. You could do that. But here, the idea was a little bit different. And the idea is off-chip load prediction. This was published in Micro 2022. It got Rahul's first best paper award. You got another one in ISCA 2024. Yeah, it's hard to get these best paper awards. And these are, I think, deserved best paper awards. I'm going to talk about this relatively quickly. Basically, the problem is long latency off-chip load requests. And we know that these are actually not good for performance. And traditional solutions, we've seen a lot of them. We've seen a lot of prefetchers. Increasing the size of on-chip cache is also important, and people are doing that. Very inefficient. These are processor-centric mechanisms, as we have discussed, although they could be applied in memory-centric systems also. But I guess one other question that's really important, I think, in future designs is, what kind of prefetcher do you use? What kind of mechanisms do you use for memory-centric systems, right? Processing using memory, processing near memory. That's a not so well-explored area, because you may still need prefetching over there, but maybe different kinds of prefetching. Okay, we're still processor-centric in this particular example. So many loads still go off chip. I already said that. 50% go off chip, even with a state-of-the-art prefetcher. And 70% actually block the retirement, so stall the processor. So let's take a look at how this access latency is constructed. So you actually need to access the caches first and then main memory. Right. It turns out if you parallelize the accesses to caches with the accesses to main memory magically, you can reduce 40% of the stalls, meaning you start your access of the cache hierarchy. At the same time, you start your access to the main memory, speculating that, oh, this is going to miss the caches, so I'm going to access memory. And if you're correct, you save, if you're always correct, you save 40% of the stalls, correct? Yeah. Now, why is this important? Because this access latency is becoming bigger with bigger caches. Right? These are some real data from some papers from 2007. You can see that on-chip cache sizes have been increasing. On-chip hit latency has been increasing. These are some data from more recent processors. Again, caches are getting bigger and slower. These are L2 latencies, but L3 latencies are even higher. So the idea is to remove the on-chip cache access latency from the critical path of off-chip loads. So if you have a load that's going to go off-chip, try not to incur the latency of the on-chip access. That's the idea, or at least expose the latency of the on-chip access to the processor. So that's the idea over here. You predict which load requests are likely to go off-chip, and you start fetching data directly from main memory while concurrently accessing the cache hierarchy. It's a prefetching mechanism because you prefetch data directly from main memory, but it's a special type of prefetching mechanism because you also predict whether something goes off-chip, right? And you could generalize it to any level, whether something is going to go to level X, right? And I guess you tried it, but maybe that's ongoing work. So how do you decide that? In this case, whenever you get a load, the question is whether it will go off-chip or it will hit in one of the on-chip caches, right? So it's a binary prediction. So a perceptron actually fits nicely to this sort of prediction because you're doing hit-miss prediction, on-chip or off-chip, on-chip hit or off-chip miss prediction, basically. Right? So this perceptron predictor predicts which loads are likely to go off-chip by learning from program information. So this is the overview. Essentially, in the baseline, you need to access every cache sequentially, and eventually the processor stalls. With Hermes, you have a perceptron-based off-chip load predictor. Whenever you get a load, you predict whether it will go off-chip or on-chip. And if the predictor says, oh, this load is going to go off-chip, it issues a request to the memory controller to start the access. And in the meantime, the cache hierarchy is accessed to verify if that prediction is correct, right? And you can see that accesses are happening. And at some point, the cache hierarchy says, oh, okay, this is correct, meaning that you actually inserted the prefetch correctly into the memory controller because this is actually going off chip. Then the cache request that is sent from the core waits until the memory controller returns the data. And when the data is returned, you can continue, you can supply the data back to the core and continue execution and update the predictor, saying that you actually made a correct prediction under these features that you used. Okay? Okay, that's the idea, basically. This way you save stall cycles because you initiate the main memory request earlier I mean, it takes time to initiate the request, of course, because there's some interconnect over here. And that is also varied in the paper. And you train, as I said. Okay, so this is a perceptron-based off-chip predictor. It uses multi-feature hash perceptron, very similar to branch predictors, actually, that are employed in perceptron branch predictors in real machines like AMD Zen 2. And the idea is you have features, for example, features that you think correlate with whether or not this load goes off chip or stays on chip, right? PC plus offset is one feature. Again, you can do feature selection over here when you try. And essentially, each weight table stores a correlation between the feature value of a feature and how it correlates with whether this load will go off chip or on chip or stay on chip. So you can see a bunch of tables, and you use simple table lookups, addition and comparison. So you extract the feature from the load request, and you get one value, PC plus offset. Let's assume it's this one. And you use a hashing function to index the weight table, and then you get some weight and sum up the weights for different features, and eventually you use an activation function, and if that activation function, let's say, activates, you predict that that load will go off chip. If it doesn't activate, meaning it's less than a threshold, then you predict that the load will stay on chip. Okay, this is the general mechanism. You can imagine features. What features do you use? Do you remember? Okay. Okay. Mm-hmm. 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 Yeah. Sure. Mm-hmm. Mm-hmm. Yeah. Yeah, exactly. You can see that you come up with some features that could be good indicators, and then you can do feature selection and simulation, and then decide which features are the most important and minimize hardware cost while getting good accuracy and coverage. That's the idea. Okay, so and then you essentially, if that decision was wrong, you train the weights, because this shouldn't be activated in that case, but you did activate it. So you actually go back and train. Okay, that's the idea. There's some training function also. Okay, is that the same as branch function? No, it's similar basically, yeah. Okay, so in the end, if you implement all of these, which is also open source, you get some performance improvements. So the orange bars are Hermes, the blue bars are what Pythia that you've seen, and you get significant performance improvement in both. Pythia has higher performance improvement compared to no prefetching, but the storage overhead of Hermes is much smaller because it doesn't use reinforcement learning. It doesn't have to store state action pairs. Here it's simple perceptron, right? Perceptron is a much simpler model compared to, it's not even multi-layer perceptron, right? It's single layer perceptron, so it's very simple. So the compared to the storage overhead, you get a lot more performance. And the benefits are somewhat additive. So you improve Pythia and Hermes, you get better performance improvements. Although you could do better with a paper that Zhenrong and Rahul wrote, which is going to appear in HPCA in Sydney, right? So you could actually coordinate these things better. In this case, there's no coordination. Pythia works on its own, Hermes works on its own. There's no information communication between them that coordinates their actions. So it turns out coordinating their actions actually provides much better performance improvements, as maybe sometime you'll talk about, but not in this lecture. Okay. Okay, so basically combining them is good for performance. So on top of Pythia, Hermes, Hermes combined with Pythia outperforms Pythia alone in every workload category. And if you had an ideal Hermes, which means that, and in simulation you can do this beautiful ideal study, you can guess that the access that you're getting in the core is going to be a miss, off-chip miss. And it can basically ideally simulate without any error, let's say, without any inaccuracy in Hermes, then you get a little bit more performance improvement. Okay. So yeah. So you get to 100% with Athena? No? Okay. Yeah. And different workloads also may fare differently. Okay. So this is the increase in memory requests. With every prefetching mechanism, you increase the memory requests, unless you throttle the prefetching mechanism such that you don't prefetch. That kind of is not a prefetching mechanism anymore, as you can see. So you can see that the Hermes is the increase in prefetch main memory requests is much smaller. That's the orange bars compared to Pythia. And if you do Pythia plus Hermes, you get a small bump. So about 6% increase. Okay, and that was the performance increase, as you remember. Okay, so this is some summary basically. So it's a very bandwidth efficient prefetching mechanism compared to an even prefetcher. Compared to an efficient prefetcher like Pythia. And we have seen earlier that Pythia was quite efficient compared to other prefetchers, right? Okay, so it's good to develop these bandwidth efficient prefetching mechanisms because they actually perform better in multi-core as well. So as you vary the memory bandwidth, this is what the curves look like. Here, I guess there are workloads that are not nice to Pythia, right? And it turns out Hermes is nicer. You can always choose the workloads that are nicer for your mechanism. That's true, yeah. Yeah, that's true, exactly. So the average, some workloads may be worse for Hermes, but on average, you don't, lose performance. Okay, something got messed up in the fonts over here, but hopefully you can read it. Okay. So in bandwidth constrained configurations, Hermes is better than Pythia. So it's more bandwidth efficient. And you combine them, you're still better in most configurations, but I guess here there's an issue that's not solved. So you can do better, basically. Is that due to the coordination? Okay, there you go. So if, the good news is I think this sort of mechanism is orthogonal to the prefetcher, right? Because you may have some prefetching mechanism and you may have some off-chip prediction mechanism that's also doing prefetching. You can combine it with any prefetcher, and these are some results you can see compared to what happens if you implement a prefetcher mechanism, and on top of that you implement Hermes. Essentially, you get significant performance improvements on all prefetchers. At least these are spatial prefetchers that are examined. So that's good, basically. It's having something orthogonal to an existing type of prefetcher is very useful. Okay, the storage overhead of this is much smaller because of reasons that we discussed, and so the power overhead. Okay, the good news is actually this is off-chip load prediction-based prefetching, which is different from the other load address prediction-based prefetching. Here, you know the address, right? You know the address, except you start the request early. You predict that it's going to be miss. Right? That's a different sort of prefetching, right? You don't try to predict the address, right? I mean, you can also speculatively decide which ones are going to be off-chip, but now you're crossing some boundary between off-chip prediction versus prefetching. It's good to somehow actually think creatively in that direction also. So off-chip load prediction can be combined with load address prediction to provide improvement as well. So this is the first perceptron-based predictor. It gets you high coverage, high accuracy, and low storage overhead. This is also open source. And you can find a lot of things that Rahul released. Did a lot of these go into the championship edge prediction? Or no? A lot of it? Okay. So you can actually test a lot of different prefetchers that people have developed over many years, including the strike prefetcher that I flashed at you, like Chen and Bear, for example, and then many other things. Any questions? Thoughts? Okay. Any questions or thoughts, Rahul? Zhenrong? No? I will say that these are actually very good directions to build on. Most of these are state-of-the-art, actually. And I mean, there's more work building on it, as I will describe in a little bit. But this sort of machine learning-driven memory hierarchy management and prefetching is a very fruitful area to develop a lot of ideas in. And in general, prefetching is a very important area to develop ideas in, whether it's in processor-centric systems or memory-centric systems. Okay, very quickly, there's more on data-driven prefetchers. There's actually work on machine learning-based prefetchers, not necessarily hardware. This work is actually software-based prefetching, learning memory access patterns from Google. Again, some more software prefetching. You can take a look at these. More recently, there's been work on perceptron-based prefetchers and prefetchers that are building on Pythia, for example. You can take a look at those also. Maybe I'll cover this one and then we'll stop and we'll cover execution-based prefetching tomorrow. So basically, it's good to look at prefetching, and it's good to look at prefetching target for specialized workloads as well. One way of looking at it is actually designing a general purpose prefetcher and specializing its parameters to the workload, like we've done with Pythia, right? And I think there's a lot of opportunity in that area. Another way of doing that is actually designing a specialized prefetcher for a particular application domain. And people have done that also. I'm going to give you a couple of examples. Graph analytics is one where people have tried to prefetch things because this is actually a very irregular memory access patterns that are hard to predict without knowing the application semantics or the graph structure. And people have tried to communicate both of those to the underlying hardware. For example, if you start going through this work list, this is the kind of thing that you're going to traverse. Right? I will not go through this in detail. I'll let you go into, let's say, more details of the papers, because otherwise we'll be talking about prefetching in the entire course. It's actually a very rich area. Even though it's a very rich area, it's still a very unsolved problem. So there's a lot more to do in this area. This is actually fascinating to me. Yeah. Okay, basically, people have done work on using data structure properties and knowledge and semantics of the graph algorithms, meaning memory access patterns, and conveying that information from the software to the hardware such that you can prefetch more efficiently. How to do that? You can take a look. Here, they have a programmable prefetcher that gets triggered based on user-defined application events. And for example, user can define a potential access pattern based on access to a specific data structure in a graph analytics application. Right? I'll leave it at that. But these are actually very interesting ideas where software and hardware cooperate. And there's more potential in this direction also. We have done some work in this area also, where these are actually general purpose mechanisms where you can communicate information about memory regions like access patterns or other semantics like compressibility, approximability, etc. But for prefetching purposes, access pattern is important. You can communicate information about the access pattern from the application to the hardware prefetcher on a per memory region basis, for example, using a general and expressive interface, which we called expressive memory. And we showed that you can actually get better prefetching performance if you actually do that. And we actually implemented this on an FPGA. It's called Metasys, where we actually looked at different use cases of communicating this information. And we showed that you can actually have a real prefetcher with real overheads on FPGA that actually outperforms existing prefetchers. So I would recommend taking a look. This second paper actually won the best paper award at HighPeak. It's a lot of implementation and very interesting work to develop on top of. Very few people go into it because of the difficulty of doing this. Okay, but difficulty should not be the reason to not do some important work. Okay, so people have also worked on prefetching for functional languages. So if you sort lists in some languages, it turns out this hinders prefetching. And people have tried to solve that problem. I'm not going to talk about that. Again, these are software, hardware, cooperative solutions. And there's more work in this area that we may talk about tomorrow. Not just functional languages, but more work for specialized languages or specialized access patterns or specialized applications that may be coming. Certainly, machine learning applications actually take their share also in prefetching, but there's more work that I didn't reference over here. Any questions? Okay, yes. Okay. Okay. Well, cache state is, in general, the data that you have in the cache and the tags, right? Prefetcher state usually is the metadata that you need to get data into the cache, let's say, right? Assuming you're prefetching into the cache. But yes, you could potentially use the tags in the cache for figuring out what to prefetch, right? And there's actually work in that area. There's work from 2000 on tag correlating prefetchers, for example. They use part of the cache state to reduce the prefetcher state. So there's work in that area. Is that what you were thinking? Yeah, exactly. So there's work. But you cannot completely eliminate the additional metadata for prefetching. You need to have something to connect the cache lines, right? But that's a good idea, I think. You can reduce the cost. Sorry, I couldn't hear.
All the memory hierarchies right now is built upon that software to be complete. What kind of states have. And I know that was made for a reason. But when we think that this is the right or a reset
Yeah. Yeah. That's a good research problem. I agree. What kind of state you're thinking of? What is the memory system oblivious to on the processor side? Yeah. Yeah. Yeah, exactly. So I think I like your idea. I mean, that goes into more data flow based principles or demand driven architectures. And I'd recommend a paper for people who are interested. This is from 1982. Treleaven. I mean, data flow machines, yes, but there's a lot of work. There's a work from Treleaven that summarizes some of it's called data-driven and demand-driven computer architecture. And there they look at different execution models. And I completely agree with you. I think we should be looking at different execution models for memory-centric systems, also for processor-centric systems, but especially for memory-centric systems, because fetching these instructions dictated from a control flow perspective is also very processor-centric. You're right, because you write some program and that's executed on the processor. But maybe if you're really data-centric and memory-centric, your data is really what should activate a function, right? As opposed to a function activating a data. So it's good to think about that. I absolutely agree. So you should look into data flow and demand-driven architecture literature more. And there's a lot of innovation and creativity that needs to be in that area. You need to be bold, though, because you'll get a lot of pushback. Whenever you try to have a different model, you get a lot of pushback, but that's fine. Okay, I guess we're done. No questions? Okay, we're done for today. Tomorrow, we're going to start with execution-based prefetching, and probably we're going to start multiprocessors as well. So I'll see you tomorrow. And don't forget about the championship branch prediction. Tomorrow, I'll have it in the slides again. Okay. Cool.